Have you ever stopped to think that every time you look at the starry sky, you're literally seeing the past? That light reaching your eyes has traveled for billions of years through space. It carries with it stories from the primordial universe. And here's the most incredible part. For the photon itself, this epic journey happened in the blink of an eye. That's right. While we perceive billions of years passing, for light, time simply doesn't exist. Light isn't just that thing that turns on when you flip the switch. It's simultaneously a wave that can spread through space and a particle that can collide with other particles. It's as if nature couldn't decide between two completely different personalities and decided to keep both at the same time. This wave-particle duality isn't just a scientific curiosity. It's the foundation of all the modern technology you use every day. But get ready, because the story gets even stranger. According to the transactional interpretation of quantum mechanics, a photon only exists when there's an agreement between whoever emits it and whoever receives it. It's as if the universe were a giant cosmic social network. Particles need to confirm friendship before they actually exist. And the most disturbing part is that this agreement can happen through time. It connects past and future in ways that challenge our basic understanding of reality. Today we're embarking on a journey that began about 13,800,000,000 years ago. It was the moment when the universe became transparent and light could travel freely for the first time. We'll discover how Einstein revolutionized our understanding of light, how Maxwell unified forces that seemed completely different, and how Feynman diagrams showed us that reality works through the constant exchange of quantum messengers. Prepare to have your mind expanded. Imagine a newborn universe where matter itself can't form. We're talking about temperatures above 100 million degrees, an incandescent plasma where protons and electrons dance violently without being able to unite. The energy is too high for any stable structure. Photons get trapped in this sea of charged particles. They ricochet infinitely, unable to travel more than a microscopic fraction of space. 380,000 years after the Big Bang, something extraordinary happens. The temperature drops to approximately 2,700 degrees. Electrons finally manage to bind to protons. The first hydrogen and helium atoms in history are formed. This process, known as recombination, frees photons from their eternal prison. The universe literally becomes transparent for the first time. However, this first light illuminates a completely empty universe. There are no stars, galaxies, or any luminous structures we know today. It's just an ocean of neutral atoms bathed in primordial light. This phase marks the beginning of what's called the Dark Ages. For millions of years, small irregularities in matter will grow slowly. These cosmic seeds will give rise to the first stars that will illuminate the cosmos. For centuries, human beings looked at light with a mixture of fascination and total confusion. Aristotle, one of the greatest thinkers of antiquity, had a curious theory about vision. He believed that our eyes emitted invisible rays that touched objects around us. It was as if everyone were a Superman with laser vision. This idea may seem absurd today, but it made sense at the time. After all, how else could we explain our ability to see distant things instantly? Islamic scientists of the Middle Ages began to dismantle these ancient theories. They realized that light came from objects to our eyes, not the other way around. They began to study lenses, mirrors, and the refraction phenomena that occur when light passes from one medium to another. It was like discovering that the world worked backwards compared to what was thought before. These studies laid the foundations for all modern optics. Without them, we wouldn't have telescopes, microscopes, or even the glasses that many people wear every day. But the great scientific battle was yet to come. In the 17th century, two giants of physics waged an epic battle over the nature of light. On one side, we had Christian Huygens and Robert Hooke defending that light was a wave. They could perfectly explain how light curved around obstacles and how different colors separated when passing through a prism. On the other side was Isaac Newton, who insisted that light was made of small particles he called corpuscles. Newton's corpuscular theory dominated science for more than a century, not because it was right, but because Newton was simply the most respected guy of the time. In 1800, a young English physicist named Thomas Young changed everything with an apparently simple experiment. He made light pass through two very small slits in a wall. The result was something that not even Newton could explain with his particles. Light created a pattern of bright and dark stripes on the opposite wall. It was definitive proof of light interference. Two light waves met and sometimes added up, creating bright spots, and sometimes canceled out, generating darkness. If light were really made of particles, this would be impossible. The double-slit experiment wasn't just a victory for wave theory, it was a complete revolution in our understanding of reality. Other phenomena began to make sense for the first time. Polarization, where certain directions of light oscillation are blocked by special filters. Diffraction, which allows light to go around obstacles as if it were water. And refraction, which makes a spoon look broken inside a glass of water. All these behaviors only made sense if light were really a wave propagating through space. But here comes the question that tormented physicists for decades. If light is a wave, it needs a medium to propagate. Sound travels through air. Ocean waves need water. So what carries light waves through empty space? Scientists invented a hypothetical substance called luminiferous ether. They imagined that the entire universe was filled with this invisible and weightless substance. It was an elegant solution, but one that would soon prove completely wrong. The truth about light waves was much stranger than anyone could imagine at the time. At the beginning of the 20th century, physics seemed to be almost complete. Scientists believed that only a few details remained to be solved. But then, a phenomenon appeared that no one could explain with the theories of the time. When you illuminate a metal plate with light, electrons are ejected from the surface. This is the photoelectric effect, and it should be simple to understand. After all, if light is a wave, you just need to increase its intensity to knock out more electrons. But reality insisted on being different. The experiments showed something completely unexpected. No matter how intense the red light was, it couldn't eject a single electron. But a weak blue light made electrons jump from the plate immediately. It was as if the color of light was more important than its intensity. Einstein realized that the only possible explanation was revolutionary. Light didn't arrive as a continuous wave, but in small energy packets. These packets, which he called photons, carried specific amounts of energy based on the color of light. Color varies according to the frequency of visible light. Each color in the electromagnetic spectrum has a characteristic frequency or energy. Blue light carries more energy per photon than green. Green carries more than red. That's why increasing the intensity of red light doesn't help. You can have trillions of red photons, but if each one doesn't have enough energy, no electron will be knocked out. This discovery demolished centuries of classical physics. But now we had an even bigger problem. If light behaves like a particle in the photoelectric effect, how do we explain the interference from the double-slit experiment? The same light that created wave patterns also collided like a projectile. Arthur Compton definitively proved this corpuscular nature when he showed photons colliding with electrons like billiard balls. The wave-particle duality of light was established. Nature had chosen to be both things at the same time, and our intuition about reality would never be the same. The discovery of light's wave-particle duality opened a Pandora's box in physics. If light could be both wave and particle, what else in the universe had this strange property? Louis de Broglie made a bold proposal in his doctoral thesis. If light, which we thought was just a wave, is also a particle, then particles should also be waves. Electrons, protons, even you yourself have an associated wave. Of course, your wave is so small that we never perceive it, but it exists. Suddenly, all matter in the universe gained a dual nature. Paul Dirac took this idea even further and completely revolutionized our view of reality. He proposed that everything in the universe is just ripples in invisible quantum fields. The electron isn't a little ball spinning around the nucleus, but a disturbance in the electron field that permeates all space. Photons are ripples in the electromagnetic field. Even you are made of ripples in various different quantum fields. It's as if the universe were a cosmic ocean where particles are just waves moving on the surface. Richard Feynman made these ideas more visual with his famous Feynman diagrams. He showed that all interactions in the universe happen through the exchange of messenger particles. When two electrons repel each other, they do so by exchanging virtual photons between themselves. It's as if they were throwing an invisible ball to each other, and the act of throwing and receiving makes them move apart. Light, in the form of these virtual photons, is literally the glue that holds matter together. Without it, atoms would fall apart instantly. The transactional interpretation of quantum mechanics adds an even stranger layer to this story. According to this view, a photon only really exists when there's an agreement between whoever emits it and whoever receives it. It's as if the universe worked through quantum handshakes that can cross billions of light years. The most disturbing part is that this agreement can happen through time, connecting past events with the future in ways that challenge our linear understanding of reality. Here we arrive at the most disturbing aspect of this whole story. According to Einstein's special relativity, as you approach the speed of light, time begins to pass more slowly. At 100,000 kilometers per second, you age noticeably slower than your friends on Earth. At 200,000 kilometers per second, the difference becomes dramatic. But when you reach exactly the speed of light, something extraordinary happens. Time simply stops. For a photon traveling through the cosmos, the journey of billions of light years happens instantly. Think about that photon we mentioned at the beginning, released during recombination about 13,800,000,000 years ago. From our terrestrial point of view, it crossed entire eras of cosmic evolution. It saw the birth of the first stars, the formation of galaxies, the creation of planets, and even the emergence of life. But from the photon's own perspective, all these events happened in a single instant. It was emitted and absorbed by your eyes at the same moment. It's as if the entire universe were an instant photograph for light. This time, dilation isn't just theory. It's a reality we can measure, and that affects our daily lives. GPS satellites need to constantly correct their clocks because time passes differently up there. If they didn't do this, your navigator would miss your position by kilometers. The light that leaves your cell phone and reaches your eyes doesn't experience any passage of time. For it, the screen and your retina are connected instantly, even though for you, the light took a few billionths of a second to make the journey. Gravity also plays with light in fascinating ways. Giant masses like stars and black holes curve space-time itself, making light follow curved paths. These gravitational lenses allow us to see galaxies that would be hidden behind others. The James Webb Telescope uses this phenomenon to observe the primordial universe, capturing light that has traveled for more than 13 billion years. Each photon it detects carries information about what the first galaxies were like, when the cosmos was still in its infancy. Light isn't just a physical phenomenon that allows us to see the world around us. It's literally the key to understanding reality's deepest structure. From those first moments after the Big Bang, when photons freed themselves from their prison in the primordial plasma, until today, when they carry information across the cosmos, light has been our main witness to universal history. Every ray of sunlight that touches your face, every star that shines in the night sky, tells a story that began billions of years ago. We discovered that light is simultaneously wave and particle, quantum field and messenger of forces, carrier of energy and information. It connects the infinitely small with the infinitely large. The same Maxwell equations that describe radio waves also explain light from the most distant stars. The photons that mediate forces between subatomic particles are close relatives of those that allow us to see the colors of a sunset. Quantum mechanics and relativity meet in light's peculiar nature, showing that the universe is much stranger and more wonderful than our intuition could imagine. Think about this the next time you turn on a lamp or look at the stars. You're interacting with a phenomenon that doesn't experience the passage of time, that can be in two places at the same time, and that carries within itself the deepest secrets of the cosmos. Light is our direct connection to the beginning of everything, our window to distant worlds, and the foundation of all technology that defines our civilization. Understanding how light really works isn't just learning physics. It's discovering how you yourself are connected to the fundamental fabric of the universe. If this journey through the world of light has awakened your curiosity about the mysteries of the cosmos, subscribe to the channel and activate notifications. There's much more for us to explore together in upcoming videos. From black holes that capture light itself to quantum technologies that could revolutionize our future. The universe is full of secrets waiting to be unveiled, and light will always be our best guide in this cosmic adventure.